Okay, continue yesterday's presentation on the smartphone application for traffic management. So after you can use the iPhone message for traffic management, you can also use information for work zone traffic. Work zone in developing country has not been addressed yet, but actually it's a daily happening issue. Okay, you go everywhere, you can see there's work zone. A work zone have safety issue involve how to place work zone sign, how to guide the traffic. Otherwise, as I mentioned earlier, if you have 4 lanes on the freeway and 1 lane closed, then I always ask students, what would be the capacity? In other words, how many vehicles will go through that segment during peak hours? And the answer is usually say, okay, 1 lane for 2,000 per lane 2,000 per lane per hour. So you have 4 lanes, should have 8,000 vehicles per lane per hour. If you close 1 lane, you should have still 6,000 vehicles per hour. But you go to do experiment. I bet you on the Route 1, you go to close 1 lane, just station your car there, all the traffic will be stuck. Answer is why. Question is why. What caused the problem? Okay, same as in work zone area. In the major work zone area, as long as you close 1 lane, then you found out the traffic completely stop. Okay, the problem is you do not have a proper work zone management plan, alignment plan, guidance plan. Then traffic cars getting there will try to change lane, weave in together, and block each other. So how to do the work zone operation is one of the issues. Okay, in the next part of the lecture, I will have some work zone mathematical model to show you. Okay, but not in today's presentation. Okay, in the iPhone application, you can also identify where is a work zone and how far the work zone is going to be. And the work zone control, we have so-called early merge control, late merge control, and dynamic control. 3 types of controls. Early merge control means what? It means you have a guidance sign to address driver to change lane much earlier advance of the work zone. Late merge control means you ask everybody to use the lane to be closed all the way to the end to change lane. Dynamic control means based on traffic condition, you can alternate late merge control and early merge control. Okay, that's not covered here, but that's the essential control strategy. Okay, in the iPhone application, again, you can identify your work zone. Found out how many work zones between your original destinations. And then what kind of control has been done on those work zones. Okay, here you can say, okay, work zone, what's your national pack, number of lane closed, heavy percentage. This information can provide you to do the route choice. Because if you know the work zone area have a high percentage of truck and the lane's work zone, in this case, it can tell you pretty much there's going to be a bottleneck area, okay? Then estimate the impact area. This the 2 ways. One, estimated by the traffic control agency, but they may not have model to do estimation. they can provide you the information to tell you what kind of work zone operation from where to where and when to when. You can do your own estimation based on your daily experience, okay? In general, peak hours, 4 lanes, if you close 1 lane, then the traffic will, the capacity may only have less than 30%, okay? Okay, so in this way, similar to congestion control boundary, okay? Work zone has a control boundary too. The difference is after you pass work zone, usually that area is what? Free flow traffic, okay? So operator can manually adjust the impact area given by the system. System means coming out from your prediction model. So you can see, given the work zone locations, you need one mathematical model to predict the queue evolution in the work zone area. Basically, given the number of available lanes and the number of closed lanes and the close distance for the blockage lanes, and based on arriving flow and discharging flow, you can estimate the queue evolutions. Confirm the estimation and try to see what would be the advisory to the advisory route to the commuters, or take any control strategy. Okay, so those work zone area, you try to minimize the number of vehicles stuck on the queue, so you may exercise run metering control. Again, those are all the control strategies you can have to use. Speed control, run metering, detour operation, signal retiming, merging control, lane-based control. That's all you have in traffic control operations. This is called the supply side control, okay? Certainly you can do a demand side control, change the departure time, change the route. That's belong to demand side control. For the supply side control, we talk about traffic control strategy. Those are all you need to know. So similar to the previous case, depending on demand level, depending on the queue. Remember, the worst case is a queue spill back to block intersections or block freeway ramps. So you try to use a management plan to prevent that happen, because once the queue blocked the intersection, then the intersection, the queue will continue to what? Not only grows and will also affect the intersect street, okay? So our control in general principle is try to prevent the queue on the freeway to extend to the on-ramp, or on the work zone could be urban arteria, okay, not necessarily freeway. So the work zone in urban arteria try to prevent the queue extend over the intersections, because once you over the intersection, and if you do not change the intersection signal timing properly, then you will cause much longer queue, again, unnecessary causing the gridlock. Okay, for example, intersection here, queue extend over here, but you signal continue the same plan. You still give there so much green time for this direction. Then what happened? Traffic have no choice. You give it green time, they keep coming and will be blocked at the street. Okay, so they keep it in mind. The basic idea is don't let queue extend to intersection or extend over the ramp area. Okay, then you can implement the plan and then see what the impact of the plan. You can easily do this kind of research by yourself. For example, if there are work zones in the Guangfu Lu, then what can you do? to detour traffic to minimize queue at the Guangfu Lu, that can be converted into a computer a graphic program and sent to all the students to let them know. Okay. Certainly, for those kind of application, you can also involve departure time choice, okay, and route choice. Okay, then this is the impact area based on the current plan. I can choose another plan to do any comparison. In those cases, in most of the cases, you may not have an optimization model to do the optimal control plan. So you can create one or two or three based on your experience, based on available route to do your comparison and just run the simulation to see the MOEs. Okay, same case. So at least take one more alternative plan and see what would be the impact. Okay, here to show the control applications. This the purpose to do what? For example, here's work zone. Okay, the question is where should you place the guidance sign? Work zone 1 for safety purpose. You want to let people know there's work zone ahead of you. So you want the traffic to slow down before they take actions to respond to the guidance work zone area. Second, in the work zone, you, depending on your strategy, you will ask driver to change lane, to merge to the open lanes. So there's a guidelines, how far away you need to give a sign, and how far away you want the driver to be alert for safety purpose. So here are the locations you need to place your sign. This work zone operation manuals. And you may want to use your model or simulation approach to evaluate if drivers follow your guidance and based on the location you place your warning sign, place your guidance sign, what would be the queue condition? Because as I mentioned several times, control depends pretty much on drivers' response to you. If drivers are not following your suggestion, then your control may not be effective. Okay, so this is this part is following the work zone operation guidelines. You can simulate and evaluate to see the actual impact. So here you see, given the work zone at different location, you should place what? Speed limit advisory, okay? In the work zone, it's also an application. It's one of the early area to do the variable speed control, okay? The idea is, you know the capacity has been reduced, right? In order for the input flow, coming flow to smoothly pass through the intersection, then what happened? The capacity has been reduced. Capacity counted as a Q. Capacity Q equal to what? K times V. So by reducing the V, which is speed, and the K pretty much will be fixed if the vehicle one by one close together. So by reducing speed, V times K becomes smaller. So that Q will be able to what? Close to the capacity. By doing so, it can reduce the Q, okay? That's the purpose of the variable speed control. And those signs is placed to let the vehicle slowly reduce speed. You don't want them to come at high speed and suddenly stop. In that way, even they are able to reduce speed, but may potentially causing work zone problem. Work zone safety is #1 issue in highway engineering and highway operations. So the question is, how many speed signs do you need? Where are the locations? You don't want to put too many, but you have to see if the speed come over here is 70 miles per hour. There's 4 lanes, you close 3 lanes, then you know what, speed will be dropped dramatically, okay? Then you know you need a longer transition segment for speed for vehicle from high speed to slowly reduce to your target speed. Okay, that is the purpose for the work zone control. Okay, that's called variable speed controls. Then based on those, there's no mature, well-accepted guideline on where to put those variable speed signs. This is still a hot, ongoing research issues. Okay. Rule of thumb, just based on the target speed, deceleration distance, and speed difference between your target speed and actual speed to compute the location for those signs, and approximately the speed difference should be at least 10 miles, because there's no point to ask driver say, oh, your speed currently 45 reduced to 40. That's 5 mile difference. It's not the it's sometimes indifference to drivers. So general principle is based on the stopping distance, okay, and based on the every 10 miles require braking distance for a driver to reduce 10 miles. So per increment differences should be at least 10 miles. But what would be the optimal number of signs and the ideal rate of change in the speed? That is an ongoing issue. It has not been finalized yet. This is an example, very typical information in the work zone. Okay, pay attention on those work zones, because in developing country has not paid much attention on this area. And usually, if you have a work zone for 1 week or couple of days, more or less they're going to have accident, 1 or 2 minor accident. Okay, so where to put signs? What sign you have? Warning sign, instruction sign. Those are different. Okay, you start with the warning sign and then the instruction sign. Here example of another sign, another operation plan. See here, we say operator select a combination of speed control and then basic control. Speed control basically just the one I mentioned, variable speed control. Then basic control, I just quickly show you what that means. Okay. If they say 2 lanes, how it close 1 lane? If you do nothing, what happens? Everyone will drive over here, right? And drive over here. And then what? This guy will change lane over here. Change over here. And then what happens? We'll slow down traffic here. You have a 3 lane, what happens? Car will change over lane here. And those guys, seeing the interference from this lane, then they will what? Change over there here. So that's why even you still have 2 open lanes, your actual capacity could be what? Less than 1 lane. Then what should you do? Early merge means you have a guidance sign. Press here, inform the drivers this lane will be closed 200 feet, 500 feet ahead. Please change the lane here. Okay, that's called early merge. So you ask drivers, don't take the lane anymore, change over here. When you see a sign, then you will see that driver change the lane. Certainly, there are still some drivers will take advantage, continue all the way to the end. Okay, that's called early merge. Another called late merge. You say, okay, work zone ahead, continue use the lane, and create a, say change lane here. They create transition zones. As the bus driver, just change your lane at the zone over here. Okay, so that's called what? Late merge. Which one is better? You do it. Which one is better? Which one should it be? Some students say this one, but this one you actually what? Completely waste the whole lane segment for queue for operation. But this one, you run the risk of what? Continue merging, interfere traffic. So which one is better? Not clear. Not clear. Actually, depending on traffic condition. If traffic is light, may have advantage one, okay? Traffic is heavy, may have the advantage one. Not clear. That's why you have a dynamic merging control. You don't need a dynamic merging control. Depending on traffic condition, mathematically tell you when you should change here. So you have two signs. One activate this area, and some condition may activate this area. If traffic condition is not heavy, actually what? Actually, you can change over here without much interference to that lane. But how heavy is heavy? Traffic control is different from planning. Traffic control, we talk about precision level is high. For planning, your difference could be 20% error, but still okay. Traffic control, 10 vehicles, difference in capacity could what? Create a bottleneck too, okay? So the question answer to you is, close one lane, given the total demand V, maybe 3,000 vehicles, what would be the capacity for this part? So this capacity is what? It's not fixed, not constant, okay? It's not constant. It depends on your supply and demand condition. So this is research, this study, and you decide where and when to place the zone control. In the worst case, we have done research and published paper. In very heavy condition, very heavy traffic volume, let's say 2 lanes close 1 lane, what's happened? Doesn't matter you later merge control, we all will be congested. If each lane have a 2,000 vehicle here, 2,000 vehicle here, if let's say freeway, you cross 1 lane, I tell you naturally this will be a complete blockage and will be less than 1 lane's capacity. So do you have any other suggestion? We found out one effective way what? In this worst case, put a temporary signal here. If you know the coming flow already over the capacity. The one I mentioned, early merge, later merge, dynamic merge is you can find a mathematical relation between the maximum output, maximum ideal throughput rate and input capacity, do a comparison. If this ideal case he used to have a 4,000, right? If the coming flow is over 4,000, close to 4,000, then either early merge or late merge or dynamic merge will not work because it's already coming over here. When we talk about early merge or later merge, is below this capacity. If higher than this capacity, what would be the most effective way? Put the signal here. Okay, we found out, put the signal here. We published paper there, has been exploratory used by some state too. Put the signal here. Basically, you have a 3 signal here. If this 2 show red, and this 2 then can move. Okay. So in this case, you will avoid what? The weaving blockage between lanes. Although you create what? Some lost time in the signal, okay, lost time, okay, but you minimize those lane change causing problem, okay. This is called signal-based work zone control, okay. Okay, so here the lane-based control refers to, I just mentioned, early merge. You may not know exactly how to control, but you need to know the concept. Early merge, late merge, dynamic merge control, and signal-based control, okay, or sometimes they call lane-based control. We don't have the signal control here. But signal control is easily use a mobile system to place the sign there. Has been used for urban arterial, but has not been used on freeway yet. The reason freeway operation agency is still reluctant, saying how makes sense if freeway will come with the signals, right? They worry about driver maybe completely shocked. How could I see the signal on the freeways, okay? So has not been used yet. But the concept will be the almost the same ideas. Again, I told you variable speed control, you guys should learn, okay? This is ongoing, very hot issue, which can be implemented easily without the investment. So configure the variable speed locations. Most effectively will be what? To combine together. Think about it. If you want the driver to do late merge, early merge control, they must have to what? Slow down the speed, right? And variable speed control will function as some advisory information. They want to change the lane, they should reduce to what kind of speed, which will have a sufficient gap created in traffic stream for them to merge in, okay? If speed is very high, then you need what? Wider gap before you can merge, okay? So speed control in general is working together with the merging control. Okay, say merge lane and take turns, okay? Here, this advanced one I mentioned, signal control. I put a signal here. It's not on the road side, okay? Simply hand on the overhead on top of the lane. So you can see, oh, my lane shows I can go, I just go. Similar to the left-hand arrows in the intersection. So you based on, so in this case, use a signal. Guarantee at least you can have a close to 2 lanes capacity. Otherwise, there will be definitely less than 2 lanes capacity. And here's advisory sign tell you we're going to have a queue, okay? And this is based on the potential queue length. Here's a road walk 1 mile ahead. If the queue already over 1 mile, then there's no point to have this sign, right? So ideally, this location is based on the maximum queue length, okay? Maximum queue length. You want to place a sign for driver to see. If you want to place a sign, driver already know the traffic condition. And then run your automation plan. Okay, see what happened. A work zone is relatively easier to control than the incident, because incident usually involves some level of urgency. Somebody died, some car broken, or something injures. In general, it's a short time period. In the simulation, you can model as a short-term event, but the work zone usually longer. Work zone cannot be finished in 1 hour or 2 hours. Okay, usually half day or 1 day, could be multiple days too. So in general, allow you to have much more time to prepare and to do a plan. That we sometimes call pre-scheduled event, and the incident we call the as an incident because we don't know in advance. Okay, here's the work. Remember here I mentioned the work zone. Remember this configuration, okay? You put a signal here, and then you need a transition period, transition segment for the driver on the vehicle on the closed lane to do a transition from lane 1 to lane 2. Okay, this distance should be sufficient for lane changes. Certainly, drivers need to follow the instruction. They are not supposed to go over these signal signs. And so based on your lane signals, you decide which lane should go first. So that's why I mentioned to you, in this operation, 2 lanes close 1 lane, almost 90% the entire area will be closed if you do not properly control the signals, if the lane volume is very high, okay? So this is the one easily implement as urban arterial. This can be a mobile sensor, okay, or mobile signals. Here is similar condition. Remember here, okay, this lane can move, this lane cannot move, okay? You assign the lane 1, lane 2, you assign different green time. Because volume and lot times may not be Q lanes, this information should based on what? Q length on different lane, okay? Drivers don't usually keep the lane balance, okay? Always one lane is longer, one lane is shorter, so you can dynamically adjust the green time here in different lane. This time in general is lost. In the intersection control, clearance time is ample times yellow face time. We generally allow people to go over, 1 or 2 vehicles to go over the yellow face. But in the work zone, we don't want them to do, okay? Prevent those cars queue here, queue this zone. So the clearance time is basically don't let them go. Use the time to actually clear traffic in this area. So this is a clear clearance zone, okay? This is a relatively new concept in the traffic engineering. Again, based on the cost-benefit ratio, safety, reliability, accessibility, and acceptability to do a cost-benefit comparison. It's not necessary to do it unless you are a very advanced company. But the work zone, more likely to do so because I told you work zone in general, you know 1 week in advance or a couple days in advance. So you can do better comparison evaluation. Also, work zone in general lasts much longer, lasts 1 day, 2 days, very common. You can see, for example, in Taipei, when they do a subway construction, how long the work zone? A couple of months, couple of years, right? The work zone in the subway construction. So whether you have a good work zone control or not, over the 1 year, 6 months period, will cause a tremendous impact on the traffic condition and the cost to the drivers or the commuters. So work zone is an important research area, and I hope you get some idea. In general, textbook does not have a work zone related study in traffic engineering. Okay, here is showing some simulation results. And based on the result, you should broadcast, convey the information to your target drivers or someone still have not taken the trip yet. Again, how to send in plans to drivers is up to you, okay? Send me by newspaper. Work zone, again, I mentioned is pre-scheduled event, so you can go through many more different medias to do your convey of the message, to do your promotion of your control strategy. It goes through the TV, goes through the radio, goes through the newspaper. They all can be done, okay? And like the incident, you have to go through the real-time information. Work zone, you don't need to convey the information to driver through real time because work zone is a pre-scheduled event. So those two natures are slightly different. Incident has to be real time for sure. Why is so slow, huh? How big area you should broadcast? This is not clear, okay? This in general, you need to know your traffic demand and traffic patterns. You want to know where the traffic will be coming to your impact area. For example, eastern part of Taipei has a construction. You don't want to broadcast to entire Taipei driving population, okay? So you should well target the geographic area and your target audience to send their information. Of course, you are lazy, you can just always broadcast. East Taipei have one two-lane closure from Street A to Street B. And those information could be a burden to some driver they don't need. For some driver they actually need it, they may not be able to hear the information because the information has no target audience and not defined clearly who should listen to those information. Too much information sometimes is what? Equivalent to no information, okay? Okay, you see, instant warning, okay, send instant warning every how many minutes, okay? And start from when to when, and broadcast duration from when to when. Okay, that's all can be pre-planned, okay? This kind of system, one is for actual operation. Second, can be used for what? Training purpose. For example, you have no idea about how to deal with work zone. And if you design such a system, can be a tutorial system to help new engineering understand what would be a step-by-step process to contend with the work zone condition, to do the work zone operation. That's why we work on those kind of, this type of the research. Step one, use as offline training tools. Yeah, most importantly, take advantage of mobile sensors, okay? It means all the drivers equipped with the GPS, cell phone, or the Bluetooth we'll mention later, okay? Yeah, just speed advisory to let driver know what would be the ideal approaching speed to the work zone. Okay, to quickly tell you data mining tools. This idea is you have so much data. What should you do to take advantage of data? Okay, that's where quickly go with this part. Okay, you want to take advantage of the data available in your database for your information distribution and for your control, okay? Your database must have all those related information, okay? As volume, all those detour route, all those information. You can take the information from your database and also based on detect information, feedback to your database to enrich your database. And allow you to do all the necessary cost-benefit analysis. In real operation, most importantly, it's not cost-benefit analysis because operation agents, they don't actually do every cost-benefit analysis for every operation. But annually or quarterly, they do need to justify the total benefit compared with the total operational cost. Okay? So academically, we do the cost-benefit analysis for every operation, but actual analysis by quarterly or by monthly, because you have agents, you spend so much money every year, and how many accidents you have to deal with, how many work zones you have to deal with, what are the impact, how many minutes delay reduced because of your operation, of your efficiency, okay? Example here is show, okay? key statistic, benefit analysis, delay, how many seconds, fuel consumption, HCCO, and NOCO2. Okay? Those are standard output for all the traffic impact studies. And here you can also have a travel time information, okay, for different OD pairs. So you can see even the model look like just a graphic interface with the users, but to support every function, you need all kinds of models. Here you can select your travel time, demand, and based on your departure time, and select origin destination, and come with your target travel time information. That's pretty much the one I'm going to convey to you. This PowerPoint is very long, so if you don't have a hard copies, yeah, you can pass the PowerPoint to you, okay? But just keep it for yourself, because this one is using for the online courses. I don't think we're going to give the PowerPoint to all the online students, okay? But you can keep this one. Hopefully this can help you develop your own business. And someday you can use iPhone information to help your country or your environment to deal with traffic congestion problem, okay? Okay, I show you some of the research, which is a relatively new research and a new business area for the traffic ITS researchers. Try to use a low-cost Bluetooth technology for the travel time, and some they try to use OD. Again, Bluetooth is a cheap, low-cost technology. What would be the potential application? Still an open domain, okay? And this is one. Currently, have a 3 to 5 companies in the United States. All are started by students, okay? One of our students, one postdoctor, they actually start the company too. And they actually promote the system. Our state has sponsored several projects. But when you read this type of article, be careful. They tend to inflate it, how good system. Indeed, the system is low cost, but need a good statistics background to do a data filtering and to get whatever information you need at the desired level of accuracy, okay? Okay, Bluetooth technology. I learned to know in Taiwan, some of the car may not have a Bluetooth, but in the United States, most cars have Bluetooth, okay? Whether you use or not, that's a different story. I have a Lexus, I have a Toyota, they all have a Bluetooth, okay? So it's a standard and short range, low power, low cost, wireless communication that uses radio technology, okay? And widespread in many types of car, you can in cell phone, in the computer, laptop computer, in car, they all have the Bluetooth. You may not know, okay? Actually, I didn't know how my car had a Bluetooth until my student told me. And send the signal range about 3 feet to 300 feet, okay? Depend the type of car, depend the Bluetooth device in your cars. So they have a different classes of the Bluetooth. Here's a summary to show you different classes and different radius. That radius dictates your detection range, okay? And the power frequency, again, that depends on your cars, have different range. But if you want to do a actual freeway control and surveillance system, I don't advise you just use a Bluetooth, okay? Because even though low cost, but the coverage is still a small percentage of vehicles. But it can be a support a supplemental system for the area with less traffic or not that important, less congestion, okay? Or in the area already have detectors, but detector spacing is too long, let's say 2 miles, 3 miles, you put a Bluetooth station within them. That could be supplemental purpose, okay? Or send the freeway off ramp, on ramp, put a Bluetooth technology as similar to AVI, automatic vehicle identification, to measure the estimate detour volume, to estimate the freeway's OD2. So cannot be, at least at this stage, cannot be a primary detection tools. Okay, this is the basic idea, okay? They have two modules. One is so-called inquiry, one called page, okay? Inquiry, basically, you detect coming vehicles and try to send a signal to see whether your car have a Bluetooth or not, okay? If your car have a Bluetooth, okay, that's good. I will take all your Bluetooth information. It's in a way similar to ID. There's ID for each Bluetooth, the ID number. So get those information and then pass through the page modules. Page module used to what? Processing, identify, or match, okay? If you detect the car with the Bluetooth, then pass this information to your page function. Page function will process those ID number and try to match your database, see whether they coming from the same Bluetooth ID or not. So the function is almost identical to what? AVI's function, okay? AVI is simply identify the incoming flows ID and try to match your database ID. The difference, AVI is actual image, okay, based on the image reader or based on the AVI's responder. But Bluetooth is passive. They take a little longer time. Here say minimum time required for discovery of all Bluetooth devices within range is 10.2 seconds. This is a weakness, okay? Because car with the Bluetooth, they are not designed for your surveillance system. They're designed for all other purposes. So we are just taking advantage of the information to your possible traffic ID, OD estimation. So this potential problem is during the detection period, if your car comes at very high speed, 10.24 seconds before you complete your processing and try to page through identification, the car already passed. So sometimes you have not finished the paging identification process. The vehicle already run over the area. So they have a trouble to detect high-speed vehicle. Vehicle comes with very high speed, okay? This is a device that's actually already done in I-95 corridor from Boston, New York to Florida, okay? So you put on the roadside, it does not need to be this way. Sometimes they put it in the radar sensor, how high your sensor, the angle of your sensor play important role for your detection precision. But the Bluetooth sensor, this is not a problem. You can be very low. You can be very low on the roadside. You can receive the information, okay? You have a system to scan the ID for each Bluetooth and try to use the match travel time to estimate the travel time between them. And there are two fundamental problems I'll mention later, okay? For design purpose, one, you need to know the spacing. Spacing, if too long, then the signal may be too slow, maybe too low, distant too far away. But if too close, could be a problem. Why? Too close, as I mentioned earlier, the detection zone could be too small. So when the Bluetooth signal sensors send the inquiry to detect whether the car have a Bluetooth or not. If car come with high speed, then if your zone only 100 feet, before you process it take 10 seconds or 8 seconds, the car already passed your detection zone. And that could be a problem. And again, if you put a multiple close Bluetooth, then could have a double count problem, because this one has not been detected but has not been processed. Then actually detected by the third Bluetooth station. Example here, if there's 1, 2, 3, everyone has the Bluetooth detection zone and detectors. The car may be detected by this Bluetooth, but should be based on the processing time and match here. But because car running too fast or your zone too short, the car may be detected by this one. So we mistakenly just mismatch the database. So the research ongoing is determine what would be the better distance between the detection stations to fully utilize the power of the Bluetooth message and to minimize the potential matching errors. And you need to synchronize all the Bluetooth time clock. Okay. So in terms of accuracy, so this is the research or the system they provided basically is provide a sensor here, reader, they call Bluetooth readers, and the data processing modules. Readers here basically is collect the information sent to the computer receiver, a computer processing and match information. You can use offline analysis or real-time analysis. Real-time analysis, the bottleneck is how quickly you respond and what sample size are useful to you. Some of my colleagues use this one to do the detour operation to see how many vehicles detour from highway actually come back to the highway. Because a lot of time you ask them to detour, they may not come back. So we use this to track. And we also use the Bluetooth technology to track in the universities big football games to see how many people coming from which entry and get out of the university based on which exit. Overall, detecting people is very useful because people walk at a slow speed. So most people have a cellular phone. So use that information to as an OD pattern is very useful. Cars is in a freeway still have some problems. As I mentioned, freeway sometimes they run at a very high speed, okay? But for local arteria, indeed they have some advantage, okay? Local arteria is relatively slow and the cost, for example, if you put a roadside radar sensor in United States, I don't know about here, in United States, the cost, each one will cost about $3,000 for radar sensors. But in the Bluetooth, just $300 to $400. Okay, 1/10 of cost. Okay. Of course, the detection rate for radar sensor in general is 90%, 95%. Bluetooth is 8%. Okay, 8 to 10%. So depending on your purpose, could have a different application. Right now, the most application used for what? Travel time purpose. Okay, and for the OD as mentioned, partial OD as mentioned. So the accuracy issues, feasibility of reporting travel time and major travel time compared to a floating car method and radio frequency RFID approach, okay, it's almost identical and cheaper, okay. Think about we do a travel time. How do you do a travel time? It's based on floating car. Floating car based on your driving speed, right? I don't know if you guys know floating car or not. You're driving, go back and forth. I try to determine number of cars pass you, and the number of cars pass by you, determine your travel time. But that's very subjective, okay? Depending on how your speed and the traffic condition you respond to. But Bluetooth approach at least objectively measure sampling vehicles. Right now they say the best case is about 8%, okay, in the freeway, 8% detection rate. And after match, they should be able to match close to 5 to 6% vehicles. So are you saying 5%, 6% enough for travel time or not? Yes, for travel time is fine. But for control purpose, it's not enough yet, okay, for control purpose. So how to extend the Bluetooth application to other control management? Still ongoing issue. Many students still working on. Every TRB meeting you can see there are quite a number of papers and ITS Congress paper talk about Bluetooth application. But most of them inflated the benefit effectiveness of the Bluetooth, okay? They don't tell you detection rate only about 8%, 6 to 8%, okay? They never talk about how many percent. So it sounds like they can detect every vehicle, which is not true, okay? Here the potential problem data collection is limited sample size. Sometimes overcounting, okay? Overcounting, just I mentioned, one car may be detected by two close space station, Bluetooth station, or they should be, you count the distance is between A and B, but identification is between A and C. So your data will not be correct. Another potential problem, you don't know traffic mode. Detect a truck or passenger car, you don't know. Okay, but with the radar sensors, roadside radar sensors, you do know what is small vehicle, large vehicle. You do know you don't know large vehicle is bus or truck, but you do know which one is a truck, which one is a bus, okay? And depending on the speed of traffic flow, you may miss some information. Or two cars very close and they send a signal all together. Right now the bottleneck is still in processing time. The Bluetooth sensor, the call reader, had to recognize the coming vehicle to see whether they have a Bluetooth devices or not. If yes, they try to read the Bluetooth ID. This process takes about 8 to 10 seconds. That's still too long. Why? Because the manufacturer of the car, their Bluetooth is not designed for your detection. Actually, they don't want to be detected by you, okay? So that part can be changed. Actually, it can be reduced to 2 to 3 seconds. But no, they don't care because you are doing the Bluetooth collection. You don't pay the cost. You are take advantage. So that part becomes a bottleneck. So you have a multiple vehicle close together. My Bluetooth devices concurrently may receive 2 to 3 Bluetooth ID come back, and they can only process one. And during that process, may cause a problem. Okay. So particular car come with the platoons. That often comes with a problem. Okay. No spatial indication, no direction indication. But you don't know the car is based on match. You don't know what direction they come from. Okay. No information outside the Bluetooth detection zone. Bluetooth, each one have a detection zone. Okay. Each one, there's a boundary. There's a boundary of detection. Look at the previous table, from 100 feet to maximum 800 feet. And this reference, you can go check the reference, okay? Here are some reference you can check. You can see a lot of IT application journals. Applications are also dependent on antenna of the Bluetooth detection detectors, okay? This is currently a bottleneck. I believe if the Bluetooth receive more market attention, this could be improved. If the manufacturer of the auto can work together with the ITS industry, they can shorten this time, okay, detection time, inquiry time. And also all the Bluetooth detectors low cost. It's produced by a company of 3 to 5 people, okay? It's all by small company, small business, super small business. So they use a very simple technology to receive the Bluetooth information. If this can be reduced to, let's say, 2 to 3 seconds, then you can increase your detection rate, particularly during the congested rush hour, okay? And traffic come with the platoons. Also, intensive interference of signal may affect the detection. Okay, some other signals around area may also affect the detection rate. Antenna is the sensor's antenna. How strong the antenna, the alignment, affect the detection of the readers. Okay, this is same as the radar sensor. Radar sensor usually there's a how high should it be, and what angle should be to cover the your target area. That's its basic design. Once you want to do the calibration, you want to make sure the radar zone come out the radar sensor, each one cover the complete lane, rather than cover half a lane or 1/2 lane. Okay, but if you do not have a calibration to make sure every radar zone cover exactly one lane, then traffic with car may be double count. For example, you have a bus, then could be counted by 2 zones. Similar problem here, your antenna do not set properly, the signal may not receive it properly, or one Bluetooth vehicle may be detected by 2 antennas, then will create a double count issue, okay? Let's talk about verification. They use a proper vehicle equipped with GPS devices, provide the ground truth travel data, okay? High resolution camera were used to obtain the travel count and travel time, for travel time and travel time accuracy comparison. So most accurate is still based on what? Based on your cell phone's GPS information. Unfortunately, that one, usually you need to get permission by the drivers, unless you have the technique like Google. Google, I mentioned earlier, they ask you, can I use your GPS information? You say yes, they will use. You say no, they still use, okay? They do have a way to track your GPS as long as your cell phone is on, in the on mode. They actually know you. Also, the information from the cell phone company, they can know where you are, okay? Based on your cell by cell, the zone position, they can track approximately you are at which location. That is why if you call 911, you don't know your location, 911 can automatically detect approximately where you are, okay? Of course, that depends on the area. Some area you have a large cell phone cell. In the urban area, usually a small cell phone cell. You call 911, you are doing some bad thing, some crime, detected by the police. They do not approximate you are in which building area. Can be as small as between the intersection block. They do know your location, not precisely. So the application, you need some technique called data filtering. Right now, the market application, this part is still have a room to improve, okay? Traffic engineer, as I mentioned earlier, in general, is not very good in statistics, okay? You ask yourself, how many statistics have you taken in your engineering learning process? So the challenge is identify outlier, okay? Some guys, because you have samples, and you want to use samples to represent actual travel time or traffic speed, then you need to know where are those samples. You are likely to detect all those slow traffic, okay? Slow traffic, slow vehicle, easy to detect. There may be a bias sample, okay? So there are sampling issue involved. Filtering technology means when you detect signal, when you see the paper or when you see those manufacturers show you the data looks beautiful, but actually it's not. Actually it's quite a lot of noise, okay? Depending on how good your car, how old your car, how advanced your Bluetooth device in your car, you'll receive a message, you see the signal quite different. It's always fluctuate. Definitely there's a lot of noise. So you have to get rid of noise. And those are the statistical approach, a more medium approach, box and whiskers filtering, traffic flow models, multiple match filters is try to smooth your data to get rid of those data noise, okay, or some data errors. So to apply Bluetooth, although the device is simple and the cost is low, but require you to have a more sophisticated statistical approach to take a full advantage. So currently, they only use for what? For the travel time application, okay? Here to show you the data filtering process from different inquiry time, and then may process to next inquiry time, okay? Next one would be better. Yeah, here I can show you. The data filtering process, okay? You have it once based on the information from your traffic simulation, one's actual data from Bluetooth, and two can do it, work together as the actual system, okay? Remember, in the simulation model, you have a data from the roadway network, you have a volume data and do the simulation. But that's volume data is coming from pre-estimate volume data. And do simulation, you come out travel time for vehicle condition from one origin to one destination. And if you have Bluetooth to support you, you can do a calibration and real-time operation. Because based on Bluetooth, even though I only have small samples, I can, based on small samples, identify the ODs. Based on that particular pair of OD to know the travel time. Assuming your statistics are unbiased, you found that travel time. I use that travel time information compared with the simulations information. And you can use that information to what? To recalibrate your simulation model and to redo your simulation. By doing so, you can allow your simulation to continuously update your parameter and let the simulation be more accurate. Because simulation, if you have a simulation, you can have any ODs, any point-to-point traffic information and queuing information and the travel time information. But the Bluetooth, you can only have what? You're out of your control. You don't know which OD you can have because depending on your samples. So Bluetooth is randomly, you can say a kind of random sampling process. You're lucky you get more samples. You're bad luck you don't get enough samples. And you get some pair of OD, but not for all the ODs. So in a way, it's a sampling OD from real-world data used back to calibrate simulation. And compare, assuming this is accurate one, and to recalibrate simulation and have a simulation update parameters. Okay, so these are the most commonly application in the traffic management. This temporal arrows I mentioned is from one inquiry related to the paging process and may come with another vehicles very close. So there's two inquiries may be overlapping. Before the device is completely processing, another one already come. And the process can be overcome if the device is more sophisticated function. Unfortunately, right now, because it's below, the actual cost is just $10 or $15, I remember. Of course, they charge you $100, okay, to $500. But actual cost, I remember, is somewhere around $10 to $15 for those cheaper devices. So those cheaper devices, processing time and recognition times is long. So if you have a large volume of vehicles all come in platoon with the Bluetooth devices and concurrently recognized by the same Bluetooth detector, could be a problem. Means too much information concurrently feed to the detector may cause a problem, okay? That's called a distribution of temporal errors. Accuracy and reliability for travel transmission. Right now, all the publications say, okay, acceptable, but that still depends on your congestion level, okay? In a light traffic condition, the information is quite accurate. At congestion level, as I mentioned earlier, it could have a problem. If the ideal condition is Bluetooth vehicles do not function together as a platoon. So when they cross the control zone of the Bluetooth, they do have a sufficient headway, allow the Bluetooth to process information. Same as you are eating some food, before you finish, another one feed you again. What are you going to do? Okay, eat two. They continue to feed again. You are not able to finish your food before they already feed you information. So the same problem happens in the Bluetooth. But that part can be overcome if the manufacturer is willing to spend more money to have a high-speed processing devices. It should be able to overcome. But other way around, at this stage, Bluetooth has not been able to prove the more valuable applications. If not more valuable applications, then stay away or potential user may not be willing to pay more money. They don't want to pay more money, so catch-22, you may not be willing to put more money invest on your devices. So right now, Bluetooth is marketing as a low-cost and limited applications devices, or as a supplemental system I mentioned earlier, work with the simulation model, work as a support component for the traditional roadside sensor. This should be rewarding that way. Only limited amount of vehicle can be detected by one Bluetooth. Okay, a data fusion technique that depend on that. You see all the common theater. Okay, those you can remember those terminology. Back to check your textbook. Okay, each one is you don't need to use all. There's just one of the candidate approach can be used to filter your data. Unfortunately, for the Bluetooth data, you definitely need to use the filtering technology to get rid of those signals, okay? Because not the traffic signal, I'm talking about the radar signals. That's the typical radar signals. They have a lot of noise. And this standard application, each detectors, they should not call loop detector, it's roadside detector, okay? Bluetooth detectors and roadside detectors you can use together to do your actual system applications. So most of the times, Bluetooth detectors used together with the actual detector. It does not need to be loop detector. You can say roadside detector, okay? Or there can be a radar detector or image detectors. And this is what to say. Application for travel time may encounter some problem, okay? Signal interruptions. A match the vehicle does not yield the travel time and may indicate turning movement. The same as AVI, you may detect this vehicle by Bluetooth 1, but the information can only be useful if you can find a match. If there are 10 vehicles detected by the Bluetooth detect 1, but only 2 detected by the Bluetooth 2, then you only have 2 data points to match. So a lot of time, they may mismatch. Mismatch could be many reasons. They say it could be turning movement, it could be just your detection problem, okay? So same as a image sensors detection, right now about 70 to 80% rate, okay? They have misreading problem. Bluetooth have more serious problem because they only detect 8%. Think about for this 100 vehicle come over here, I detect 8%. Another 100 vehicle detect 8%. For 8% to 8% to match together, the probability is low, right? That's their problem, okay? That's a problem. So in a short distance, and that's more likely they can detect stable detection rate. In the longer distance, 800 or 500 feet, they detect 8% detection rate. You may match nothing, okay? Fortunately, they can continue to match with low cost. So let's say for over the 5 minutes period, the first minutes, the 8% may match nothing. And second minutes, the 8%, they can match 5%. So overall, in the 5 minutes period, a summation of the probability, they can still have enough information to do a travel time estimation. And that is a reason so far they can only use for travel time estimation, okay? Cannot be used for control purposes. You still need a roadside detector or image detector if you want to do a traffic count, traffic volume for your control operation purpose, okay? And you need, this talk about statistical approach, okay? You need all the statistical procedure to filter the data. For example, you could match 20 vehicles in location A, detect 20 vehicles in location A, found 5 vehicles in location B, and out of those 5, only 3 match with those 20 vehicles. That's not uncommon, that's very common, okay? And how are you going to base on those 3 matched information to reach some reliable conclusion? It's a challenge by statistics, okay? So this Bluetooth application is still at a very early stage. For travel time, because if they can claim I match 1%, 2%, well, that's still okay for travel time. Because if you do a probing vehicles, it's less than 1%, 2%, okay? Work zone application, they also do work zone applications, okay? Work zone is, they have a chance to apply successfully because work zone usually slow speed and the area coverage is well defined. So relatively easy to detect the work zone travel time from A to B, okay? And route choice, that's the one I mentioned, is sampling issue, okay? But think about even you are doing a survey, roadside survey, or you check the license plate, still sampling, okay? So Bluetooth argued they are all another way of low-cost sampling strategy. I mentioned earlier, you want to know how many people follow your detour guidance, so you can detect how many people get off the ramp. And at on-ramp area, use Bluetooth to see any matching rate or not. Okay, so still a sampling problem. The better way is you have a license reader, okay? Can read the license plate. That's you can up to 7 to 80% detection rate. Again, data filtering, those used for OD estimation, okay? Those are the OD arrows, OD information. Right now, there's another area application is use the cell phone information combined with Bluetooth, because may not able to have so many people work together with you to join your cell phone club, but you can get some people to work with you. So you have one source information from your cell phone information. It's a sample too, but that's actually OD. You also have information from your Bluetooth information. You may have some information from your small number of detector information. So compile all the information and combine all together, integrate information, become a multi-source database. And that is a hot area they call big data analysis. They intend to have a one, GPS information, second, Bluetooth information, third, traffic radar detector information, fourth, image sensor information, and some partial AVI information. Combined together, become multi-source information to identify one, travel flow speed, second, vehicle composition, of see what percentage are truck, what percentage are passenger car, as the basis for the traffic control data. That's called big data issue, okay? Big data is now popular everywhere, and the research has been evolved to the transportation and traffic control too, okay? So it's a direct sample of the travel time without necessity to incorporate a model for traffic dynamics, okay? That's also provide information to verify your traffic flow models if you do have. Here's they show how they apply this for OD estimation, okay? Historical OD metrics, use a simulation, and then you can participate OD and use a Bluetooth information to find out whether they estimate OD in some particular OD can match with the Bluetooth OD or not, okay? Raw choice is, again, examples. It's not reliable at this stage yet. The one I show in Ocean City, one freeway, one is local arteria. My colleague has done the experiment there, try to detect how many vehicles match the route at the freeway, how many take the arteria, okay? Bluetooth is one way to do it too. In every major holiday or major event day at the university always put a Bluetooth at entry and exit. Try to see how the traffic flow pattern within university, okay? We don't know how they work in the university, but we do know which entry they come, which exit they get out, okay? That's partial ODS estimation, but not exactly raw choice yet. They can do what? They can do the purpose to tell you your model is wrong, but they cannot tell you your model is right, okay? Because let's say Bluetooth detects some OD, takes some route, but your model does not show you have some OD take this route, then we know your model is wrong. But we cannot tell you your model is right, because Bluetooth data is so small sample. They can, in the best case, they still have not been reported to over 10% of the samples in all the literature and so far. But they still have an advantage. You can roadside, you can put so many Bluetooth. So segment by segment, you can still see the travel time variability. over the different segment of the highway. Okay? That's Bluetooth potential applications. That will tell you what kind of model they use. If you only have limited data from Bluetooth, again, you can try to fit into a mathematical model or statistical models. Use that model to generate to different applications. Okay, so basically, that's what I'm going to tell you, a simple idea. All you need to remember is this one. Okay, this is the most important one you should remember. This roadside unit is do the experiment to see what is the best spacing between the stations. This is not predetermined because this pretty much depends on most of the cars, what kind of Bluetooth devices they have, how strong the signal send out. So if you are doing actual operations, you need to try and error to experiment the spacing between 300 to 800 feet. See what the space can minimize double count or minimize processing error. If the space I mentioned earlier too short, what's happened? When the car come over here, the Bluetooth devices just try to recognize the Bluetooth information ID, then your car may already move out of the zone, okay, before they actually recall your ID and allow this ID to match with next detection station ID, okay. But if too short, too long, then the message may be too weak, okay, or concurrently in the zone may have what? In that detection zone, may have multiple vehicles, may have 223 vehicles concurrently within the detection zone. And unless the processing time is sufficiently fast, they could concurrently receive 223 vehicles ID and need to be processed. Okay, so too wide, too long, and too narrow is still a problem. Okay, unfortunately, as I mentioned, this is not controlled by your detector. How good your detector? One of the factor uncertainty is by your car. This car may be a 1980s car. This car may be 2010's car. These two cars, Bluetooth function devices, power are different. So for the devices to receive those information, one could be very weak, one could be a different noise. So a lot of uncertainty. The one main reason is those Bluetooth in the car, they are designed for their own purpose. They are not designed for you, okay? And that's the main purpose, okay? Main reason. And you take advantage of their information without paying the cost. But they are talking with the manufacturers of autos and the United States or the IEEE and Auto Manufacturers Association and Federal Department of Transportation in the United States to try to set a standard, as I mentioned, for those automated vehicles or connected vehicles. If those cars are connected vehicles and they in general have a very reliable, stable message for you to detect, because connected vehicles are supposed to have a function easily detected by roadside infrastructure and can talk to you, so certainly you can identify those cars easily. But if they have an automatic vehicle, with those systems, they don't need your Bluetooth devices, because they automatically will be tracked by the control center to know your speed, okay? So overall, Bluetooth is still Still for a poor state, cheap area, and low-cost application for the general traffic management does not require high precision. That should be okay. Okay, next time maybe you can buy one, or Dr. Zhou want me to bring some traffic counter devices back, okay? If I remember, I made one Bluetooth devices and the roadside traffic counter back. So you don't need to go out to collect data. You don't need to stand at the intersection, do your dummy count, okay? You can just play tube there, maybe more tube. Then get 24-hour data, come back. Make sure nobody steal your counter, okay? That will be fine. That happened. Sometimes your counter will be stolen by some people for some reasons. Just want you to remember all those applications needed to be supported by mathematical models. Okay, done. Good night. Thank you.